In physics, space-time is any mathematical model that combines space and time into a single interwoven continuum. The space-time of our universe is usually interpreted from a Euclidean space perspective, which regards space as consisting of 3 dimensions, and time as consisting of 1 dimension, the 4th dimension. By combining space and time into a single manifold called Minkowski space, physicists have significantly simplified a large number of physical theories, as well as described in a more uniform way the workings of the universe at both the supergalactic and subatomic levels. Explanation. In non-relativistic classical mechanics, the use of Euclidean space instead of space-time is appropriate, because time is treated as universal with a constant rate of passage that is independent of the state of motion of an observer. In relativistic contexts, time cannot be separated from the 3 dimensions of space, because the observed rate at which time passes for an object depends on the object's velocity relative to the observer and also on the strength of gravitational fields, which can slow the passage of time for an object as seen by an observer outside the field. In cosmology, the concept of space-time combines space and time to a single abstract universe. Mathematically, it is a manifold consisting of events, which are described by some type of coordinate system. Typically 3 spatial dimensions, and 1 temporal dimension are required. Dimensions are independent components of a coordinate grid needed to locate a point in a certain defined space. For example, on a globe the latitude and longitude are 2 independent coordinates which together to uniquely determine a location. In spacetime, a coordinate grid that spans the 3 + 1 dimensions locates events, i.e., time is added as another dimension to the coordinate grid. This way the coordinates specify where and when events occur. However, the unified nature of space-time and the freedom of coordinate choice it allows imply that to express the temporal coordinate in one coordinate system, requires both temporal and spatial coordinates in another coordinate system. Unlike in normal spatial coordinates, there are still restrictions for how measurements can be made spatially and temporally. These restrictions correspond roughly to a particular mathematical model which differs from Euclidean space in its manifest symmetry. Until the beginning of the 20th century, time was believed to be independent of motion, progressing at a fixed rate in all reference frames. However, following its prediction by special relativity, later experiments confirmed that time slows at higher speeds of the reference frame relative to another reference frame. Such slowing, called time dilation, is explained in special relativity theory. Many experiments have confirmed time dilation, such as the relativistic decay of muons from cosmic ray showers and the slowing of atomic clocks aboard a space shuttle relative to synchronized, earthbound inertial clocks. The duration of time can therefore vary according to events and reference frames. When dimensions are understood as mere components of the grid system, rather than physical attributes of space, it is easier to understand the alternate dimensional views as being simply the result of coordinate transformations. The term space-time has taken on a generalized meaning beyond treating space-time events with the normal 3 + 1 dimensions. It is really the combination of space and time. Other proposed space-time theories include additional dimensions, normally spatial, but there exist some speculative theories that include additional temporal dimensions and even some that include dimensions that are neither temporal nor spatial. How many dimensions are needed to describe the universe is still an open question. Speculative theories such as string theory predict 10 or 26 dimensions, but the existence of more than 4 dimensions would only appear to make a difference at the subatomic level. Space-time in literature. Incas regarded space and time as a single concept, referred to as pacha. The peoples of the Andes maintain a similar understanding. The idea of a unified space-time is stated by Edgar Allan Poe in his essay on cosmology titled Eureka that space and duration are one. In 1895, in his novel The Time Machine, G. Wells wrote, "There is no difference between time and any of the three dimensions of space except that our consciousness moves along it, and that any real body must have extension in four directions. It must have length, breadth, thickness, and duration." Marcel Proust, in his novel Swann's Way, describes the village church of his childhood's Combray as a building which occupied, so to speak, four dimensions of space, the name of the fourth being time. Mathematical concept in encyclopedia under the term dimension. Jean La Ronde-D'Alembert speculated that duration might be considered a fourth dimension if the idea was not too novel. Another early venture was by Joseph Louis Lagrange in his theory of analytic functions. He said, "One may view mechanics as a geometry of four dimensions, and mechanical analysis as an extension of geometric analysis." The ancient idea of the cosmos gradually was described mathematically with differential equations, differential geometry, and abstract algebra. These mathematical articulations blossomed in the 19th century as electrical technology stimulated men like Michael Faraday and James Clerk Maxwell to describe the reciprocal relations of electric and magnetic fields. Daniel Siegel phrased Maxwell's role in relativity as follows: "The idea of the propagation of forces at the velocity of light through the electromagnetic field as described by Maxwell's equations, rather than instantaneously at a distance, formed the necessary basis for relativity theory." Maxwell used vortex models in his papers on non-physical lines of force, but ultimately gave up on any substance but the electromagnetic field. Pierre Duhem wrote, "Maxwell was not able to create the theory that he envisaged except by giving up the use of any model, and by extending by means of analogy the abstract system of electrodynamics to displacement currents." In Siegel's estimation, this very abstract view of the electromagnetic fields, involving no visualizable picture of what is going on out there in the field, is Maxwell's legacy. Describing the behavior of electric fields and magnetic fields led Maxwell to view the combination as an electromagnetic field. These fields have a value at every point of spacetime. It is the intermingling of electric and magnetic manifestations, described by Maxwell's equations, that give spacetime its structure. In particular, the rate of motion of an observer determines the electric and magnetic profiles of the electromagnetic field. The propagation of the field is determined by the electromagnetic wave equation, which requires spacetime for description. Spacetime was described as an affine space with quadratic form in Minkowski's space of 1908. In his 1914 textbook The Theory of Relativity, Ludwig Silberstein used biquaternions to represent events in Minkowski space. He also exhibited the Lorentz transformations between observers of differing velocities as biquaternion mappings. Biquaternions were described in 1853 by W. R. Hamilton, so while the physical interpretation was new, the mathematics was well known in English literature, making relativity an instance of applied mathematics. The first inkling of general relativity in spacetime was articulated by W. K. Clifford. Description of the effect of gravitation on space and time was found to be most easily visualized as a warp, or stretching in the geometrical fabric of space and time, in a smooth and continuous way that changed smoothly from point to point along the spacetime fabric. In 1947, James Jeans provided a concise summary of the development of spacetime theory in his book The Growth of Physical Science. Basic concepts. The basic elements of spacetime are events. In any given spacetime, an event is a unique position at a unique time. Because events are spacetime points, an example of an event in classical relativistic physics is the location of an elementary particle at a particular time. A spacetime itself can be viewed as the union of all events in the same way that a line is the union of all of its points. formally organized into a manifold, a space which can be described at small scales using coordinate systems. A spacetime is independent of any observer. However, in describing physical phenomena, each observer chooses a convenient metrical coordinate system. Events are specified by 4 real numbers in any such coordinate system. The trajectories of elementary particles through space and time are thus a continuum of events called the world line of the particle. Extended or composite objects are thus a union of many world lines twisted together by virtue of their interactions through space-time into a world braid. However, in physics, it is common to treat an extended object as a particle, or field, with its own unique position at any given time, so that the world line of a particle or light beam is the path that this particle or beam takes in the space-time and represents the history of the particle or beam. The world line of the orbit of the Earth is depicted in 2 spatial dimensions x and y and a time dimension orthogonal to x and y. The orbit of the Earth is an ellipse in space alone, but its world line is a helix in spacetime. The unification of space and time is exemplified by the common practice of selecting a metric such that all 4 dimensions are measured in terms of units of distance, representing an event as or where is the speed of light. The metrical descriptions of Minkowski space and space-like, light-like, and time-like intervals given below follow this convention, as do the conventional formulations of the Lorentz transformation. Space-time intervals in flat space. In a Euclidean space, the separation between 2 points is measured by the distance between the 2 points. The distance is purely spatial, and is always positive. In spacetime, the displacement for vector delta r is given by the space displacement vector delta r and the time difference delta t between the events. The spacetime interval, also called invariant interval, between the 2 events, S2, is defined as where c is the speed of light. The choice of signs for above follows the space-like convention. Space-time intervals may be classified into 3 distinct types, based on whether the temporal separation of the 2 events is greater, time-like, light-like or space-like. Certain types of world lines are called geodesics of the spacetime, straight lines in the case of Minkowski space and the closest equivalent in the curved spacetime of general relativity. In the case of purely time-like paths, geodesics are the paths of greatest separation as measured along the path between 2 events, whereas in Euclidean space and Riemannian manifolds, geodesics are paths of shortest distance between 2 points. The concept of geodesics becomes central in general relativity, since geodesic motion may be thought of as pure motion in spacetime, that is, free from any external influences. Time-like interval for 2 events separated by a time-like interval. Enough time passes between them that there could be a cause-effect relationship between the 2 events. For a particle traveling through space at less than the speed of light, any 2 events which occur to or by the particle must be separated by a time-like interval. Event pairs with time-like separation define a negative space-time interval. The proper time interval would be measured by an observer with a clock traveling between the 2 events in an inertial reference frame. When the observer's path intersects each event as that event occurs, light-like interval. In a light-like interval, the spatial distance between 2 events is exactly balanced by the time between the 2 events. The events define a spacetime interval of 0 all have light-like separation. Given one event, all those events which follow at light-like intervals define the propagation of a light cone, and all the events which proceeded from a light-like interval define a second light cone. Space-like interval. When a space-like interval separates 2 events, not enough time passes between their occurrences for there to exist a causal relationship crossing the spatial distance between the 2 events at the speed of light or slower. Generally, the events are considered not to occur in each other's future or past. There exists a reference frame such that the two events are observed to occur at the same time, but there is no reference frame in which the two events can occur in the same spatial location. For these space-like event pairs with a positive space-time interval, like the proper time of time-like intervals, the proper distance of space-like space-time intervals is a real number value. Interval is area. The interval has been presented as the area of an oriented rectangle formed by two events and isotropic lines through them. Time-like or space-like separations correspond to oppositely oriented rectangles, one type considered to have rectangles of negative area. The case of two events separated by light corresponds to the rectangle degenerating to the segment between the events and zero area. The transformations leaving interval length invariant to the area preserving squeeze mappings. The parameters traditionally used rely on quadrature of the hyperbola, which is the natural logarithm. This transcendental function is essential in mathematical analysis as its inverse unites circular functions and hyperbolic functions. The exponential function, a real number, used in the hyperbola, generates hyperbolic sectors and the hyperbolic angle parameter.